Happy Pi Day, everyone. This is the Pi Machine. It's a device that progressively approximates the value of pi and prints it out digit by digit. The longer you let it run, the more digits that come out and the more accurate its approximation gets. All the while, you get to enjoy blinking lights, a bell ding on each digit, and lots of clicking. Since yes, all the computation going on inside this machine is being done by electromechanical relays. But anyways, pi. I mean, everyone likes pi. It's gotta be the most famous number in popular mathematics. Or at the very least the most famous transcendental. And what's not to love? It's got a name far too easy to pun on dessert items, something about a circle I guess, and all those digits. Pedants will argue that every number has an infinite expansion of digits, but for any rational number, those digits end up repeating, and a lot of irrational numbers you see are just square roots of a rational number. Pi is transcendental, which means neither of these apply, and though we haven't proven it yet, pi also appears to be a normal number, which means the digits are as good as random. And yet, pi is one specific set of random digits that ends up all over mathematics. As one might expect, there's a proud history of computing this series of digits to greater and greater precision. There's the single fraction approximations like 22/7 or 355/113, usually worked out through geometric reasoning, but things get even more precise when you define pi as a sum of fractions, since the further you carry out the sum, the tighter your approximation will get. It's approaches like these that let Isaac Newton compute 16 places, Ludwig van Soilen to compute 32, and engrave it on his tombstone, and much later let William Shanks set the record for by-hand computations of pi with 707 digits over the course of his life. Though sadly, due to human error, only 527 of these were correct. But that was back in the 1800s, when work was done with pen and paper. Things really took off once mechanical computation came on the scene. Suddenly, one person with a desk calculator could compute over 1,000 digits, and with electronic computers, that same 1,000 digits could be computed in the order of minutes. Then it became hundreds of thousands, then millions, billions, trillions, and at our current rate, I wouldn't be too surprised to see us surpass the quadrillionth digit of pi within a decade or so. I've always liked the idea of a machine that could do one of these pi approximations right in front of you, kind of like Bornock's Pi Spigot, where you can get the digits of pi literally on tap. Absolutely charming. But one of the things I just couldn't get over is how you can never be sure with one of these things that the creator isn't just cheating. And by cheating, I mean it's just as easy to store the first 10,000 digits of pi in the device and then stream them out one by one. That's not computing, that's just remembering. Impressive when humans do it, sure, but computers, that's just lame. Now, to be clear, as far as I'm aware, the Pi Spigot is legit, but it got me thinking. If there's one thing this world needs, it's a pi machine you can be sure is doing the computations right in front of you. Something you couldn't miss if you tried. Something clicky. When it comes to digital logic, it's hard to get much simpler than the relay. It's a form of switching that predates integrated circuits, transistors, and tubes, since it's just a regular mechanical switch but articulated by an electromagnet. Commonly, relays will have a dual-throw arrangement, so that the center switch jumps between one of two contacts, depending on whether the coil is active or not. In a way, a relay is a way for a circuit to rewire itself, kind of like a railroad switch. And in doing so, with the right connections, they let you do things like make a circuit that inverts its input, make a circuit that only turns on if both the inputs are on, make a circuit that latches itself on whenever it gets a pulse, or even one that generates pulses. All the logic gates you're used to from digital electronics can be made out of relays. And with enough of them chained together, you can even start to do computation. In fact, the very first electrical computers were built on relays, before work shifted to the considerably faster vacuum tube. Doing math with relays works the exact same way you learn arithmetic in elementary school, except being in binary, it actually ends up being even simpler. Now I'm sure a number of you would strongly disagree, but think about it. In base 10, even to do single-digit addition, you need to memorize how to sum 100 pairs of numbers. In binary, there are only 4 combinations, and it's easy enough to reduce them down into just a few logic operations. With just 2 relays, you can make a circuit like this one, which adds 3 1-bit numbers into a 2-bit output. And just like with by-hand addition, if you want to add numbers bigger than a single digit, you can just chain the smaller addition operations together with carries. The same works here. String a couple of these adder circuits together, and you can start adding 4-bit numbers, 8, 16, as wide as you want. This works well for relatively short numbers, but it still costs 2 relays per bit, which means if you want to add really long numbers like 128 or 256 bits, this circuit gets really big and really expensive. But remember, a 4-bit adder is really just 4 copies of the same circuit doing the same logical operations. We could just as easily reuse one adder and feed in the inputs for each column one at a time and get the same output. In fact, as long as you have some form of memory to pass the carry bits from the last column into the next one, we can set up one adder to add really long numbers one bit at a time. For each pair of add-in bits you stream in, you'll get one bit of their sum. The cool thing here is that there's no longer a length limit to the numbers this circuit can add. It could be 1 bit, it could be 5 bits, it could be 1,000. They all take 2 relays. The only trade-off here is time, since the wider the number is, the longer it takes to work through all their bits. We can do the other basic arithmetic operations with relays too. Subtraction is really similar to addition, a bit shift is basically a multiplication by 2, and you can combine several additions with bit shifts to get multiplication by any number. In a similar vein, division can be reduced to shifting bits and subtracting. It works by using the same long division algorithm, except remember how you needed to guess what the next digit would be, then do a multiplication to check? Well, in binary, that multiplication is either by 0 or 1, so guess and check boils down to just check. To divide a by b, you shift in a 1 bit at a time, and every time your accumulator is greater than b, the next output digit is a 1 and you subtract b. Otherwise it's 0 and you leave it alone. In other words, the logic is shift in the numerator, subtract if you can. Using the building blocks we've already established, it's pretty easy to make a circuit which, given a denominator, takes the numerator bit by bit and outputs the quotient bit by bit. What's neat about this circuit is that watching the internal bits, you can see it get into loops, like here. What you're seeing is the binary version of a repeating decimal. Just like how in base 10, 1 over 3 is 0.33333, in base 2, it's 0.010101. You've probably noticed that for some of this wiring, I'm using printed circuit boards rather than doing everything by hand, and it's for good reason. Relay logic circuits can very quickly devolve into wiring spaghetti. Check out one of my first attempts at a relay computer from years ago that I tried to hand wire. This board is functionally equivalent to these 4 printed ones. Now, purely hypothetically, I want you to imagine that there was a bad component right in the middle of all this. Yeah. Even on neater breadboards, with all the mechanical action going on, these relays like to loosen themselves up and jump right out of the sockets. Try debugging a circuit like that. That's why this time around, I decided to design some common modules into PCBs to clean up the wiring. Things like adders, subtractors, counters, memory circuits, selectors, and a couple LED panels for debugging. These boards boil down a lot of the repetitive wiring to printed traces, and they even line up the input and output connections, so a lot of the signals can be carried over ribbon cables 8 bits at a time. This was actually my first time doing PCB design, and I gotta say, it turned out way easier than I thought it would be. All you have to do is design the circuit board you want in KiCad, and then lay out the components on the board. The software will tell you what pins need to be connected, and then it's up to you to route traces between them like the game Free Flow. I find it makes for a pretty enjoyable puzzle, though maybe if I was a professional electrical engineer working on much harder routing problems for circuits with far stricter tolerances, this process wouldn't be quite as fun. At this point, we've got the relays, we've got the arithmetic circuits. How do we wire all these things together to actually approximate pi? Luckily for us, there are plenty of different ways to go about this, from empirical methods to Monte Carlo methods, and a slew of different infinite summations. The algorithm I chose is a relatively recent one known as the Bailey-Borwein-Plouffe formula, first discovered in 1995, and it looks like this. You can get it from some weird integral tricks, which I think Michael Penn does a good job of explaining. What's most notable about this formula in particular, though, is that it gives an efficient digit extraction algorithm for pi. You can actually use this formula, with a few manipulations, to compute any arbitrary digit in pi, like say the 10 millionth, without actually having to work out the preceding 9,999,999, just as long as you're okay with the digits being in base 16. BBP isn't the fastest converging approximation of pi, but the superpower of being able to pick out arbitrary digits makes it really useful for confirming the results of other algorithms when doing long computations of pi. In our case though, I'm going to use the original summation, no fancy digit extraction tricks. And the summation itself is actually pretty eerily well suited for the binary system. All the multiplications are powers of 2, like 8k plus 1 in the denominator. It's the same as taking k, shifting it over 3 bits, and filling in a 1. Dividing by 16 to the k is the same as shifting 4k bits to the right. All the numerators of the fractions are powers of 2, so you guessed it, bit shifts. And maybe a bit more subtly, each iteration of the summation has 4 terms, which we can number with exactly 2 bits. All those observations make this formula in particular a lot simpler than others to implement in relays. Pull out all the bitwise operations, and there are really only two arithmetic operations that we need: division and addition. The relays here work in two passes for each term. One works out the long-form value of each fraction, and the other adds that value into the accumulator. The only other thing I needed to add was a circuit to count up for each value of k, and use that to fill in the denominators. That's the really cool part about there being exactly 4 fractions. If you use 2 bits to determine what fraction you're on, the whole state machine is just a counter. The lowest bit determines whether to divide or add, the next 2 bits pick which fraction to use, and all the upper bits fill in for k. The other neat thing is that thanks to the bit streaming tricks from before, this circuit can carry out the calculations to as many decimal places as you like. The only limiting factor is the number of bits for k. Well, and we need somewhere to store the approximation of pi while it's being computed. I mean, at 4 bits per decimal digit, you'd need one more of these boards for every 2 added digits of precision. And pretty soon the majority of relays in the device would just be there to act as memory. Boring. Plus, I'm not up to soldering all that. Instead, this is where I cheat. All the computation happens on relays, but some of the storage happens on an appropriately named Raspberry Pi. But, let's be clear here, only storage and generating clock pulses. You might say that me asking for your trust here is a little ironic, considering the goals of this project. Anyways, here's how the PCBs hook together. This section counts what iteration we're on, this section does the division, and this one does the addition. The part in between the rest is the glue board, since it passes signals between all the other components and the Raspberry Pi. And on the Raspberry Pi, there's a short program that reads from the machine and displays the output on screen. Let it run, enjoy the blinky lights, all the clickety clicks, and sure enough, that's pi we're getting. Being able to see the results converted to decimal also helps to demystify what exactly is going on with each pulse. You can watch the result for each division get closer and closer to the real value the more bits get written out. Having a better look inside the machine also helped a ton with debugging, which, believe me, there was a lot of. I mean, look at this wiring. The PCBs do a lot to organize things, but even then, it's still a bit of a rat's nest, and it's way too easy to get wires crossed plugging one board into another. Even with the PCBs there were problems. One of my designs actually has a defect in it, where during routing I accidentally made a trace that crossed positive to negative. I didn't even notice until I built the board and plugged it in. Luckily this one ended up being salvageable, since I was able to physically sever the traces and handwire a jumper around them. When it comes to bugs though, the absolute biggest contributor here are the relays themselves. After all, relays are mechanical objects, and that gives room for lots of failure modes. I'm lucky enough mine are sealed on the side, so I don't have to relive the moth-filled days of yore, but heat and mechanical wear are still very real problems. Originally, one of my boards was designed to run at 12 volts, but with all the active relays on it acting like little heaters, it would get pretty warm in a short amount of time. Not very long into its life, it actually mechanically broke, and now just generates binary gibberish. Now everything runs at 6 volts and is a fair bit cooler. The other annoying thing is that the memory latches do occasionally like to stick, ignoring whatever bit was actually supposed to be stored. This one adds a frustrating level of non-determinism that seems to be brought about by high clock rates, bad choices in voltage, and, of all things, gravity. In my testing, I found one way I could seriously reduce my error rate was to stand the boards up sideways rather than laying them on their backs. No kidding. Relays are fickle things, and since I was getting a little annoyed at long streams of calculations getting ruined by a single misplaced bit, I added a tiny bit of error correction to the Raspberry Pi. Now, the Pi runs the calculation in tandem with the relays, and if it detects an error, it resets the relays to a clean state and starts that section over again. Don't worry, the computation is still all happening on the relays, this just helps smooth out the occasional glitches in this electromechanical hardware. And to be clear, I have seen this thing run almost an hour without a single error occurring. The last two things I felt this machine really needed were a bell to ding on every successive digit, and a printer to spit out an ever-growing tape of pi. This one is a thermal receipt printer being controlled by the Raspberry Pi, but believe it or not, the conversion from binary to base 10 is still happening on the relays. Base conversions like that aren't too bad for small integers, but they get kinda tricky for really long fractional values, since a single binary digit can touch many decimal digits. The trick I came up with is that each time a digit is computed, I pick off the integer part of the approximation and then multiply the whole thing by 10. So for instance, we pick off the 3 and continue approximating the value 1.4159. Then take off the 1 and approximate 4.1592. Each time, the next digit is in the integer part of the number, so it's always easy to extract. And don't worry about the multiplication by 10, since that's really just 2 bit shifts and an add. It costs all of 4 extra relays to compute, and takes no extra time since it runs in parallel with the addition step. It's incredibly minor, but that hack has got to be my absolute favorite in this machine. But anyways, let's take a look at this whole thing in action. Press the start button and it's off. And every once in a while, it spits out a digit. As for speed, well, this thing is definitely not setting records anytime soon. At the fastest, I've had it running at 32 clock ticks per second, though 20 Hz is much more stable. The runtime also depends on the number of digits you want to compute, since more digits means more iterations, and each iteration needs to be computed to more digits of precision. For 6 digits though, it takes under 2 minutes. For 16, it's about 10 minutes, and 32 takes well over a half hour. It has a quadratic complexity, which means that to reach digit 4096, which is the furthest this machine should be able to compute by my estimates, it would take about a year and a half of non-stop operation, assuming nothing breaks and I don't go absolutely crazy from all that loud clicking 24/7. That same computation on my computer takes about a second. But hey, building relay computers hasn't been about speed since the 1940s. And besides, we already know pi to trillions of digits. For this machine, it's all about the process, being able to stretch out the computation into a more human appreciable timescale. Savoring the computation, one might say. Though that one would not be me, since that sounds irredeemably nerdy. Anyways, there you have it, the relay-powered Pi machine. I'm gonna be honest, this project was a tricky one, but I'm pretty happy with how it turned out, and I learned a lot from it. Pi approximations, PCB design, relay logic, laser cutting, and let's not forget all those crazy bitwise manipulations. Which reminds me, there is one last ability of this machine which I've so far neglected to mention. I mean, we all know a left bit shift is basically a multiply by 2, and so it's really cheap to take the value of pi we've computed and shift it, and basically, yeah, this machine has a tau mode. I don't necessarily endorse it, but like, come on, it was just too easy not to implement. And all I could think about was doubling my ad revenue when June 28th rolls around. Anyways, happy Pi Day.